Swayam Prabha. Digital India. Educated India.
Today we will be doing the torsional vibration using the finite element method. So, basically I will be introducing the finite element method which will be useful for purpose of the analyzing the torsional vibration. We will not go into more detail on the finite element method as such, but how it can be used for analyzing the rotors for torsional vibration we will try to highlight. And then we will, through some examples, we will try to see how this particular method is having capability to analyze more complex rotor system as compared to either analytical method or Newton's method. The transfer matrix method we already seen, it can handle large systems of rotors. And so, let us see what are the things we will be covering in this particular lecture. So, we will be analyzing the torsional vibration by finite element method. Free and forced vibration, both we can able to do it with this method. Various concepts of the finite element methods like elements, nodes, field variable, degree of freedom of a node or of an element, interpolation or shape function, and two conditions which we need to satisfy of the interpolation function, that is a compatibility condition and the completeness condition. Based on these we will be choosing the interpolation function. So, we will introduce these terminologies, and then once we discretize the system into various elements, how to obtain the elemental equation, and from those elemental equation how to get the system equation and application of the boundary condition in the system equation, so that either we can able to solve for free vibration or forced vibration of the torsional vibration. So, now with a very simple case we will try to see how the finite element method works. In the continuous system approach we have seen that the governing equation defines for each and every particle onto the system. So, that particular equation represent the governing equation for the whole system. But in finite element method we will see that we will first discretize the system, we will break the system into various pieces, and then we develop the elemental equation for each of them, and then system equation can be built. So, let us take one case in which we have a cantilever shaft like this. One end of the shaft is fixed, another is free. For finite element method we need to break this particular shaft into number of pieces depending upon the accuracy required. These size of each of the shaft segment can vary. Here I have taken uniform. So, if total length of the shaft is L, each element, because we are divided into 5 element length, if it is uniformly divided, in that particular case we will be having length is equal to L by 5, and each of this shaft segment will call these as element. So, element 1, element 2, element 3, element 4, element 5, and between the two elements there is a common interface, and those we call it as a node. So, we have node 1 here, node 2, node 3, node 4, node 5 and node 6. So, these are the node positions, and in finite element method we will try to find out the solution at these node positions, and we will see that we will be if we want the solution in between, we will be using some kind of interpolation function to obtain that. And if we want to develop the elemental equation, so we can take one of the representative element and we can draw the free body diagram of that. So, if we draw the free body diagram of one of the element, so let us say this is the one of the element, I will enlarge it. Let us say this is the eth element, and to define the location of this element, I am attaching a coordinate system which we call as local coordinate system. In the actual system, we can have a coordinate system which is, I should call this as capital Z. So, this is defining a axis system which is global axis system. This is local to this element. Now, the length of this element is L, small l. Our node here is, let us say, ith node, and this is jth node, and at each of this we now want to specify the field variables. So, obviously field variable is at ith node we have angular displacement phi z I, and here angular displacement phi z j, and their directions we are taking in left to right as positive. So, both are having the same direction at two nodes at j and I and j. Apart from this, we will be having the torque associated with this displacement. So, I am writing here torque as T. This is the reaction torque from the other element. So, T r I, and here T r j. The direction of this torque is also same as the displacements. We are taking same as the displacement, and depending upon their actual direction, the positive or negative will take care of the actual direction. So, this is an element of the shaft system for torsional vibration, and you can able to see that at each node one field variable, that is the angular displacement, is there. So, this particular node is defined by this field variable, a single field variable for this particular problem. This is another node, there also there is another field variable. So, for one element which we have considered here, there are two nodes and the elemental degree of freedom is 2. So, one is phi z1, phi z1, and another is phi z j. Now, because whatever the governing equation we derive for continuous system, which was valid for each and every particle in the whole system. So, obviously, that governing equation will be valid for this element also, but in this particular case, as I mentioned, we will be seeking the solution at the nodes only, and if we want the solution in between, solution means the angular displacements in between, then we will be using some kind of shape function. So, that means in this particular case, this particular shape function in finite element method is generally a polynomial. So, this is the angular displacement of an element. So, superscript E is representing this is the angular displacement for one element, which is function of both axial position and time. We will be representing this as a polynomial. So, polynomial will be having some constants like a, bz plus cz square. We can take this as several terms depending upon the problem. We need to truncate this polynomial up to certain degree of the polynomial. So, you can able to see that in this interpolation function some unknowns are appearing, and these unknowns we will be finding from the boundary condition of the element, because this solution which we are assuming is for this element. So, we need to find out these constants from the boundary condition of the element. Now, once we have chosen the solution in this form, so we can able to see that in this particular case boundary conditions is z is equal to 0. Here we have angular displacement of the element at z is equal to 0 is phi z I, and at z is equal to L, other end of the element, we have this angular displacement at L is phi z j. So, we expect that these constants will be in terms of these field variables at node I and j. So, that means this particular solution which we is in a more general form can be written like this: phi z element zt is equal to, here we can able to write in terms of some functions which is function of z. There could be several functions. Number of functions will govern by the type of problem we are dealing with, but in general we can able to write like this, and here we can have various field variables. So, this is a more general representation of the assumed solution, in which we have taken r number of field variable. For the present problem r is 2. So, we expect only 2 terms here and 2 functions here, and this in more compact form we can able to write this as n this is for the nodes. So, you can able to see these field variables are defined at nodes, node 1 to rth node. For present case r is 2, so up to second will be coming. So, n e is representing that these field variables are at the nodal position. These are the function of z, which will be of the form of polynomial, and actual form of this will be obtaining depending upon the boundary condition of the present problem. So, this is the solution for the element, and we can able to appreciate here, because we are using polynomial and we need to truncate the polynomial at some degree. So, this solution is approximate in nature. So, once this solution is approximate in nature, if we try to satisfy this solution into the equation of motion, so obviously that equation of motion will not satisfy completely. There will be some residual, and now we'll be trying to see how this assumed solution, approximate assumed solution, can be substituted in the governing equation, and how we can able to derive the elemental equation for the element which we have chosen. So, we will be using a Galerichan method for this. In this particular method, whatever the residual comes after substitution of this assumed solution in the governing equation, we minimize that particular residual. So, let us say R is the residual for that particular element. So, we multiply this by some function. So, in Galerichan method we multiply by these functions, which are we call as shape functions, and we integrate this quantity over domain or whole length of the element, and we equate it to 0. So, that whatever the residual is there, that is distributed over the length, and because we can have these shape functions are in number depending upon the degree of freedom of the element. So, that many equations will be getting from this method. So, now let us see what is the form of the residual. The shape function will at present keep in the general form, and subsequently we will be obtaining the explicit form of this particular shape function. So, let us see the residual, because we earlier derived the governing equation which was having this form for continuous system. So, this is double dot derivative with respect to time. This is function of both z and t. Then I am representing the double derivative with respect to z as comma double z. So, that means phi z, this is same as like this. So, this representation is more compact. So, I am using this representation, and this phi is function of z and t. And if we have external torque which is function of which is distributed torque, so this one, or if we have concentrated torque at particular location in this particular element. So, this will be function of time only, and we will be using the direct delta function z minus z naught location. So, here if the torque is within the element, then only it will contribute, otherwise it will not contribute. So, if z naught is within the element, then only it will be appearing. Similarly, the external torque which is distributed, if it is there within the element, then it will be having contribution in the equation of motion. So, this equation of motion which we written earlier, only difference here is you can see instead of only phi z, I am writing the superscript e. So, that means we have written this for element, because this governing equation is valid for each and every point on the system. So, it is valid for this element also. So, you can able to see this is the this is representing for the element, and because these solutions are approximate, so this will not be perfectly 0, and this quantity we will call it as residual, which is function of z and t. So, the whole quantity is residual. Now, we want to minimize this particular residual as we using the Galerichan method by multiplying by the shape function and equating it to 0. So, this is the Galerichan method. So, now I am substituting the residual which is here in this in the next slide, and so I will get terms like this. So, within bracket the residual I am expressing. So, this is the residual term, basically this is the inertia term and this is elastic torque term, comma zz means double derivative with respect to z, then external torque which is distributed, and concentrated torque which is located at one location at z is equal to z naught. So, this was the residual. We are integrating this and over the domain and equating it to 0, where this I is from 1 to r depending upon the degree of the freedom of the element. Now, in this particular equation, because we are using the assumed solution in the form of polynomial, you can able to see that here we have second derivative involved with respect to z. So, whatever the polynomial which we need to choose, that should have at least quadratic term. So, that means because if you are taking up to only the linear term a and b, the second derivative of this term will give this quantity 0. So, here this term will be 0. So, this is not a complete representation of the polynomial of the assumed solution. So, for this particular case you can able to see at least we need to go up to the quadratic polynomial. We can take more also, but at least quadratic is required. But by some mathematical manipulation we can able to reduce this particular differential order. That we will see how we can able to reduce the differentiation order, so that we can able to use lesser degree polynomial that will be having a lesser requirement in the computation. So, let us see how we can able to. So, what we will be doing? We will be doing basically integration by part of this term with respect to z. So, first term is as it is, there is no change in the first term. Only terms containing the double derivative with respect to z, we are doing integration by part once. So, here I am writing this in more explicit form, 0 to L G j d z, and other terms n I is there, T external distributed and T naught, which is concentrated torque. Okay. So, now I want to do the integration by part of this term. I am doing this separately here. So, this term will be as it is minus in this let us say n I is the first part and remaining is the second part. So, we can write this as G j n I, this is the first part, integration of the second part, that means phi z, one derivative will reduce here and limit is 0 to L, then because is negative here 0 to L, we can have differentiation of the first part and the second part integration dz, and the torque term, this external torque term will remain as it is equal to 0. So, main term which we have manipulated is the second term. So, you can able to see this is the first part, integration of the second part, limit, and then differentiation of the first part and integration of the first part. So now you can able to see in the whole expression the phi z is having derivative of single only. So we could able to now use lesser degree polynomial without compromising on the terms. So you can able to see even if you are taking a linear polynomial, the terms will not vanish, and this particular requirement is called the completeness requirement. Of shape function. So we have seen that how we evolve the requirement of the shape function. One of the requirement, that is a completeness requirement, that so we should choose the polynomial such that when we substitute in the formulation which shown, it should not vanish. So in the formulation, we after the integration by part, we could able to reduce the order, and that is why this particular step is called weak formulation in the finite element method, in which from polynomial requirement to the linear requirement of the shape function we could able to reduce. So this requirement we could able to weaken it. So that is why this particular step is called weak formulation. And you can able to see now that now we can able to have the explicit form of the shape function. To get the explicit form of the shape function, obviously now we have seen that the linear polynomial is good enough for this particular problem from the weak formulation. So now we will obtain the explicit form of the this shape function using the boundary condition of the element. So for this case, we chose one element and we had ith and jth node, and there the field variables were these two, phi z I and phi z j, and local coordinate system was z. So we have boundary condition that at z is equal to 0, phi z I is phi z is this for element, phi z e, all are element because we are representing for this particular element only. Similarly, at z is equal to L, we have another boundary condition, that is phi z j. Now, once we have the form of this elemental field variable in the form of polynomial, as we have seen in from the weak formulation, okay, this is good enough, and you can able to see that there are two constants and we have two boundary condition. So in that way also we can able to obtain the explicit form of A and B in terms of this nodal displacements. So first condition, if we satisfy here, so we will get this as phi z pi for element. So A plus B into 0. So from here we can see A is phi z I, and from the second boundary condition we have this A plus B L, and that is equal to phi z j, this one. And now we already know A is this one, so B can be written as phi z j minus phi z I for element divided by L. So you can able to see that we could able to obtain the A and B, and this we can able to substitute in this equation, phi z I plus phi zj, this is for all for element, phi zi divided by L, and z is here. So the assumed solution now contain the field variables and the z, which is polynomial. So this equation we can able to rearrange, we can able to collect the terms of the phi zi which are here, and phi j is single term. So we can able to write this as this assumed solution in the form of polynomial can be written as 1 minus z by L phi zi plus z by L phi zj. Now with some manipulation we can able to express this as 1 minus z by L. This is representing a row vector. This particular symbol is representing a row vector, and this is representing a column vector. So you can able to see, if we multiply these two vector, we will get the same expression as the previous one. This is the column vector, this is the row vector. Now if you recall, we wrote this as earlier n1 z and 2 z, and here we have the same thing. And these n1 and n2 are the shape functions, and these are the nodal displacements, and we wrote this in the more compact form as shape function row vector and the field variable at nodal location. And now we will see the property of this two shape function. If we see n1 is 1 minus z by L and n2 is z by L, if we see the element having this axis, total length is L. So if you want to plot the n1, so let us say if you want to plot n1 here, so at z is equal to 0, which is this location, the value of n1 is 1, so this is 1, and at z is equal to L, this quantity becomes 0, so is here, and is linearly varying in between. So this will vary like this. N2 at z is equal to 0, it is 0 here at z is equal to 0, and at z is equal to L is having one value, so is one value, and in between is varying linearly. So you can able to see that how this interpolation function changes, and from this we can able to obtain the so this is Ni, and this is corresponding to node I, and this is corresponding to node J. So you can able to see that if we want the value of this field variable at z equal to 0, this will be 1, this will be 0, and that will be giving us the field variable at ith node. If it is z is L, and I will be 0, this will be 1, so we will be getting the field variable at the jth node. But if we put z in between, then it will interpolate the field variable from this field from these nodal displacements, and we can able to get the field variable at any other, or the angular displacement at any other location. So basically here all these corresponding to the I and jth node are there in the previous case also. So, now we have seen the property of the shape function. We have obtained the explicit form of the shape function for this particular element, in which only we had two nodes and we had 2 degree of freedom of the element. Now, we will see another property of the shape function which we need to satisfy, and that is the compatibility condition. The compatibility condition is between two nodes or two elements. We have seen the completeness condition we satisfied within a particular element, but this compatibility condition we need to satisfy two elements at the common node. So, if we have two neighboring elements and there is a common node in between, then let us see what is this compatibility condition we need to satisfy. So, basically we have divided the shaft into various elements and we have drawn the free body diagram of that, and during assembly obviously we need to join all those elements, and during joining there has to be some compatibility, that the displacement predicted by one element at one particular common node and displacement predicted by another element at the same node should match. That is the compatibility condition. So, let us see through how we should whether this particular shape function which we have chosen is compatible up to the requirement for us. So, in this particular case, basically if we go back to our equation, a weak formulation equation. So, in this within the integral, whatever the highest derivative of the field variable is there, we need to satisfy the compatibility condition one order less. So, this is the, I should say, thumb rule, that within the integral in this weak formulation we have first derivative of the field variable. So, we need to satisfy the compatibility condition one order less. In transverse vibration, we will see that these derivatives will be having higher order, and we need to satisfy even higher order field variable derivatives. But for this torsional case, only we need to satisfy the compatibility of the field variable itself. There is no need to satisfy for the its derivative with respect to z. So, with this rule of the compatibility condition, let us see how we can able to check this condition for the chosen shape function. So, we have two neighboring elements, element E and element E plus 1. The common node is J, this one is I node, J and K. J is the common node between these two elements. So, now for element E, we can able to write the field variable using the shape function. Here you can able to see they are corresponding to node I and J field variable. Similarly, for element E plus 1, the expression this is the field variable for E plus 1, shape function remain the same, and here the field variable at the nodes will be J and K. So, using these two we can able to predict. So, from first we can able to predict the displacement, angular displacement in the E element, and from second we can able to predict for the Eth element. But at common node we can able to predict from this element also and from this element also, and we need to see that this prediction should be same or not. So, let us see for Eth element, if we substitute J is equal to L, which is corresponding to the jth node. So, if you see back for this element, for J is equal to L, this is the node, this is the local coordinate system. So, if we put Z is equal to L, this N1 will be 0, and I will be 0, and J will be 1, and if we multiply this, we are getting the field variable at the jth node. Now, if you take element J plus E plus 1, then the jth node location this is the E plus 1 element. Local coordinate is again starting from the same point here, but node is j here and k here. So, you can able to see that for element E plus 1, the jth node is at z is equal to 0. So, that is why we are trying to predict the field variable at jth node by putting z is equal to 0 in the E plus 1th element equation. So, in this particular case n j will be 1 and this will be 0, and you can able to see after multiplication we are getting the field variable at the jth node. So, both elements are giving the angular displacement at common node as same. So, we call these as they are compatible. So, this is the compatibility condition satisfaction. So, whatever the polynomial we have chosen in the form of shape function, they are compatible for the present problem. Now, once we have chosen the explicit form of the shape function, you can able to see the previous equation which we had for I is equal to 1 to r. We had r such equations because ni was there in each of the expressions, and those equation we can able to put in a single equation in the vector form. So, here now r is 2 for present case. So, this is the same weak formulation equation which we are putting ni in the form of a vector. So, you can able to see the form of n will be for present case n1 and 2. So, basically if you expand again, you will get two equations out of this. Similarly, here because there was derivative with respect to z. So, I am writing this as basically this expression is n1 comma z and 2 comma z. Comma z is representing that we need to derivate the shape function with respect to z once, both the shape functions. And here this is the other term which is after integration by part we got an additional term, and these the external torque terms, distributed torque and the concentrated torque. So, this is the term which we got after integration by part. So, this limit shows that particular term. Here also we have put the all those ni in a vector form, so that we can able to represent this in a more compact form. Now, having obtained the shape function, and in this particular equations we need the derivative of this with respect to z of shape function. So, the shape function we can able to derivate once, and because only the shape function will get differentiated, this is time dependent. So, this will not get differentiated with respect to z. So, this is the field variable which is function of both z and t. This is the field variable at node which is function of only time only. So, this is the difference. So, this is for the whole element, this is for the element, that is why it is function of time only, and in between we interpolate using this interpolation function, and this comma z is representing derivative with respect to z. So, because we know the form of this, so we can able to differentiate this to get 1 by L and 1 by L, because we know once we differentiate we will get this quantity, because z was there, 1 is constant, that will vanish. Similarly, if we differentiate with respect to time, this term will get derivated and will be. So, these two terms we can able to substitute in the above expressions. So, this I am substituting. So, you can able to see I am getting a row a column vector of n and row vector of n from this, and because this is time dependent, so it can come out from the integral. Similarly, from second expression, this is row vector, column vector, row vector, which is coming from here, and this time dependent term I am keeping outside. And here I am writing in a more expanded form like this, and this is a torque, external torque. So, I am keeping this as it is. Now, you can able to see the same equation I have written in more explicit form. This is exactly same equation as previous one. Only thing here I am substituting for the limit. So, in previous case we had this one, and I am substituting the limit. So, in this you can able to see for z is equal to L, this will be 0 and 1 will be 0 and 2 will be 1. So, this will give me this, and similarly for z is equal to L and 1 will be 1 and 2 will be 0. So, we will get this. So, basically these are the reaction torques at the two ends of the shaft, which I am representing as this particular vector. And this term I am calling as a mass matrix. This term I am calling as a stiffness matrix, and remaining this term I am expressing as the external torque term. So, this is the reactions, because we have divided into element, and this is the element, this is the external torque. The explicit form of this mass matrix will be like this. So, if we multiply this, this will be the explicit form of the mass matrix. Similarly, the stiffness matrix we can able to multiply. So, this will be the explicit form of the stiffness matrix. This we already expanded the reaction torque terms. So, this will be reaction torque term at one of the ith node, and this for the jth node, and this is the external torque. So, in the present lecture we have seen how to formulate the elemental equation for torsional vibration. We started with the very basic concept of the finite element method. First we need to discretize the system into various parts that we call it as element, and we took one of the element and we obtained the governing equation that we call it as a finite element equation for that. And this particular finite element equation, the form is similar as we have standard equations in the vibration, which contains the mass matrix, stiffness matrix, reaction torques and external torque. Damping we have not considered in this particular case. And once we obtain this elemental equation, in the next lecture we will see how these elemental equation can be used to analyze more complex system, or how we can able to solve a system equation, because this equation is representing for one of the element. So, similar equation we need to write for all the element in the system, and then we can combine them, and then boundary condition can be applied to get the system equation, and that can be solved for either free vibration or forced vibration. So, you can able to appreciate once we take up with some example how this particular method is can tackle various kind of boundary conditions, and even for large system the formulation is easy. So, is more once we have these elemental equations ready, we can able to make a computer program for analyzing more complex system, and that we will see in the subsequent class.